Hello, it's Keith here, and this is lesson 41 of the platform-specific series of my Z80 programming tutorials. Now this one's taken a little bit of a while. We're going to be looking at the CRTC again of the Amstrad CPC, and we're going to be looking at a technique that is known as Rupture. This is quite complicated, and one of the main things it's used to do is create split screens. But first, before we go into that, we're going to have to actually discuss the screen in more detail. And hopefully through doing this, you're going to understand a bit more about what clever tricks the CRTC can be fooled into doing that exceed what its intended purposes were, because that's why Amstrad CPC games are suddenly so impressive. It's because people are manipulating the chip, the CRTC chip, and making it do things that the CPC really shouldn't be able to do. But unfortunately, the disadvantage of this is you're actually having to do a lot of the work of the CRTC chip yourself in software. And we saw this a little bit before with my tutorial on using the EGX graphics mode, which is where we change screen modes every other line, and this tricks the screen into showing a kind of 320 by 216 color screen. But this week we're going to go into a lot of other things. So first, let's have a look at the CPC screen as a sort of concept. Now, I've created this, I actually created it in LibreOffice's spreadsheet tool. Now, this is a kind of synthetic representation of the screen here. So the first thing to understand is that the screen actually works in 8 by 8 pixel character blocks, effectively mode 1 character blocks. So if you imagine that we've got our visible screen here, and this is our bitmap screen, you can see I've kind of drawn the Amstrad CPC boot screen here, and you can see it just here. So that's kind of our screen. And this lighter area in the middle is the area that we can draw to, the bitmap screen, where we can show our sprites and things. Now, of course, outside of that, we have the border. And this goes on a physical CRT to the edge of the actual plastic of the screen. But there is actually other areas during the draw cycle that we can't see. There are these off-screen areas, and also there are some things known as H blank and V blank. And these are the times that the beam, the physical beam that would be drawing on the CRT is moving back. Because, of course, if you don't know for some reason, the CRT has a sort of gun inside it that scans across the screen, illuminating the pixels on the screen, and it kind of moves in a zigzag. It goes from the left to the right, moves down a line, keeps going, gets all the way to the bottom, and then starts back at the top again. And it keeps doing that to keep the image visible. So that's how things work. And of course, the CPC's graphical hardware has to work within that capability, because that's what is needed to get on the screen before we had TFTs. So we've got our visible area, we've got our border, we've got our invisible area, and we've got our H blank and our V blank. Now, of course, on the CPC, we have 6 interrupts per screen. Now, these happen actually every 50-second line. Now, in most cases, everything works within equal multiples of character blocks. There are a total of 39 invisible lines, there's a total of 25 visible lines, and so on and so forth. But in this case, it actually works in pixel lines, and the interrupts occur every 52 for pixel lines, which means they don't truly line up to character blocks, which is quite annoying. You can see that this interrupt here appears halfway through block 7 here. And this one appears pretty much at the bottom of block 13, and so on and so forth, which is very annoying, but that's the way it is. Now, technically speaking, there is no way of changing the time the interrupts occur. They always occur every 52 lines. However, there is a very dirty trick, which I'm currently unable to get working properly, known as RVI, which is where we create a very strange screen that is effectively multiple lines on a single line. And this tricks the interrupt into visibly appearing at a different place, although technically it still occurs on the 50-second line. We're not going to cover that yet because I haven't got it working, but we are going to cover how to do split screen today. So this is kind of our conceptual screen here. This is our areas, and as I've said, it all works in 8 by 8 pixel character blocks. So we've discussed CRTC registers before, but I've updated my table with a little bit of extra information here because we are going to have to go into things in more detail, and I'm going to have to zoom out a little bit, which I know everyone hates because they try and view on phones and things, but you're going to have to bear with me. We've got too much information today. So I've added some extra information, and I've also added this extra column, CRTC Limitations. Now, if we get our WinApe up here, and if we go to debug, settings general is it? I think here it is. Now you've got this option here, CRTC type. You'll see there are actually 5 different types here. Now during the life of the Amstrad CPC, the manufacturer of the CRTC chip changed, and some of the manufacturers did things slightly differently to others, probably to save some money and things, so they don't actually quite work the same. This is fine for the normal Amstrad CPC because they all work the way the CPC expects to. But when we start pushing the rules to the limit or breaking the rules, some of them don't work in the same way as others. And we do have some limitations, and I'm trying to document them here. They are very complicated though, and in some cases they're a bit weird. Some of the CRTs, for example, if your screen is slightly too small, if your screen is not exactly 39 character blocks tall, if it was 38.5, some don't care, some do. So we have to kind of find some settings that work on all of them, because it's okay if you're writing a demo to only to work on CRTC 1 or something, but if you're writing a game, I think you're really going to have to try and find something you can use on all of the CRTCs, otherwise you're going to be cutting out a large percentage of your market. Now, these are the CRTC registers that we've kind of looked at before. We're going to be looking at them again later, but the new thing we need to discuss is these internal registers. You see, while there were some registers that we can change and on some of the CRTC functions read back, though some CRTC modes can't read back, so we're not going to be looking at that. But while there were registers that we can change, there are also registers that are internal. Now, these are things like the current position of the beam, and these are important when it comes to debugging our code, because as I said before, we are, to some extent or another, we're going to have to actually create the screen ourselves rather than letting the CRTC chip do it for us, because we're going to trick that CRTC chip. And that means that if we do things wrong at the wrong time, maybe our screen's going to go crazy. So we need to understand that these registers exist and know how to monitor them. So let's have a look at that now. So here's our WinApe, and if we go to debug and if we select registers here, we get this new window here. And what's this? Well, we've got here the CRTC registers just here, and we've got the internal registers just here. And also what we've got is this row highlights. If we tick this, we don't immediately see anything happen, but if I then pause the emulator here, you can now see we've got this vertical line here. And this is actually the position of the beam that's physically drawing the screen here. And if we watch these, we will see the registers change as we move along. So if I just keep pressing F7 here, you can see the beam is moving physically along the screen. Now, I've just cycled things on a little bit because before you could only see this horizontal line, but that was because the beam was currently in the off-screen area here. Now you can see we've got a kind of cross here, and so we can see the exact pixel that is being drawn, or rather the exact sort of group of pixels that make up the character blocks. You can see it's moving along fairly quickly as we are going down. As I said before, each character block on the screen is effectively one no operation. So some of these commands are more than one no operation worth. This is worth about 3 here. So you can see we're jumping in large chunks here. But you can see as I'm cycling through the code, you can see that the beam is moving across the screen and gradually down. So how do these registers actually relate to the visible screen? Well, I've kind of drawn a little representation here again. So we've got the kind of bitmap screen in the middle here in this light blue, the border in the dark blue, the off-screen area, and then the horizontal and vertical blank here. So if you imagine this yellow line here with this blob here is the actual beam and the current pixel that's being drawn, you can then see how our various registers are working. So the first thing is we've got the width of the screen itself, including the border, and this is the horizontal total, register 0. The bitmap area is the horizontal displayed, register 1. The vertical total is the total height of the screen, including the invisible areas. Now this really has to be fixed, otherwise we're going to get a screen that shakes like crazy. Then we've got the vertical displayed here. Now if we're counting it in pixel lines, this is made up of R6 times R9 plus 1, and the reason for that is that R9 is our character height effectively, but when it says 7 here it actually means 8, that's why there's the plus 1. And then because the height is represented by 25, which is the number of character blocks, the number of pixel lines will be made up by that multiplication there. We also have the horizontal width and the vertical width here. One important thing to notice though is the vertical sync width on CRTC 1 and 2 is fixed to 16, but that's not going to be something we're going to mess with today. That's something that becomes more required with RVI and really dirty tricks like that. So that's not something we need to worry about at this point. Now, the one that's probably most interesting to us today is the display H&L. This is the source data of the screen, the bitmap screen. Now, the real important thing and the reason why we want to start messing with it is this data, and a few of the other registers as well, are only read in at the start of a screen. So if we change the address in register 12 and 13, halfway down the screen, it won't change. It would only change on the next screen, so we'd end up with a page flip rather than a split screen. Now that's not what we want, so how do we get around this? Well, what we have to do is we have to trick the CRTC. What we can do is we can do this trick which has become known as rupture. This is where we tell the system that the screen is half the height of the actual screen we want. The CRTC chip will start drawing that screen, and then just as it finishes that first screen, we then change all of its registers and say, well, actually there's this new screen and it's the rest of the height, and here's the memory address of it. And the CRTC isn't really very smart. It doesn't realise, well, hang on a minute, I've just finished my screen. It then just starts drawing this second screen as well. And what we effectively have is we have two screens, the first one with our first memory address and the second with our second memory address. But of course, we have to time this at exactly the point where the first screen has completed, give or take. But we have to have our Z80 do the work of changing all of these registers every single frame that's drawn to the screen. The timing has to be pretty precise. There's some flexibility with, at least with this trick, but with things like RVAI there really isn't. But in this case, we don't really have to be too precise. We just need to make sure we've got the new screen defined as the last one ends, and then it will draw a second screen. When the second screen completes, we then need to reset everything so that the screen finishes and starts again correctly. Now, it is important to notice that when we're doing all of this, we have to make sure the height of the screen is correct. We need to have the equivalent of 39 character blocks, 312 pixel lines to our screen. If we don't, things are going to go crazy, especially on some of these CRTC versions. Some will get away with a 311 line screen, some will not. So we need to be precise on that, and we need to make sure everything works consistently. So we need to be synchronized to our interrupts and things if we're using interrupts to make sure this effect happens. So that's what we want to do. We want to have two split screens. What's our procedure for doing this? Well, the first thing we need to do is we need to make sure we're synchronized. We need to start changing things at the top of the screen when the screen starts redrawing. So we need to synchronize things and make sure we're as tight as we possibly can be. Next, what we're going to do is we're going to disable the Vsync. Now, the Vsync happens at the bottom here. Why are we doing this? Well, we don't want the Vsync to occur after we've defined our first screen, because we're going to define a second screen. So we need to trick the Vsync into being disabled, and we'll turn it back on later on. So we set the Vsync position to 255. Now, usually our Vsync position is 30. A Vsync position of 255 is never going to happen. It's a trick to disable the Vsync, so the Vsync is now effectively disabled. Now what we're now going to do is we're going to do a set of commands relating to this first screen, and we're going to do them later on to do a second screen. So we're going to set the height of our miniature screen here. We're then going to want to set a memory address, assuming that we are doing this to do that. You know, if we want these to have different memory addresses, we're going to do that. And then we wait until the beam gets to the bottom of the screen, either with lots and lots of no-ops. Remember that 64 no-ops is the equivalent of one line, or we can use interrupts, which is what we'll be doing in today's example. And once we've got to the bottom of this screen, we then repeat this procedure, defining the next screen. Now, of course, depending on the height of these screens, eventually we will run out of vertical screen space. At this point, we now need to have that actual Vsync. So we set the Vsync position. We're going to set it to 0. This will force the Vsync to occur. And then we just need to wait until the gun gets to the top of the screen again. Once the beam's at the top of the screen, we then are able to start redefining these screens, because, as I've said before, the important thing to understand is we have to do this every single frame. If we don't do it right every single frame, and if we're not precisely timed, our screen's going to flicker, roll, go crazy. It's not going to be pleasant. So that's what we have to do. Now, there are some rules here. The main one is the screen must be 312 lines tall, otherwise the synchronization is not going to work. We have to be very precise in our timings. We can't be a bit out, otherwise, say, the screen's going to go crazy. When we define a screen, it can't physically start before the last one ends. This is what I said before. The CRTC isn't going to read in things like register 12 and 13 until a new screen starts. So we do have to make sure we do that correctly. Now, when we define our screen heights, we're defining them in character blocks. Our character blocks in today's example are always going to be 8 tall. You can change this, but it does cause a lot of confusion. It makes your maths more difficult, and it might not help in some cases. I do have a more complex example that we're going to look at in a later lesson where we do use 2 pixel tall character blocks. This will be a setting of 1 because it's always -1 in register 9. But I believe setting this to 0 doesn't work on some CRT modes, some CRTC types. Maybe there's a cleverer trick than I know to do it. I should point out with all of this, this is really the absolute limit of my ability. I'm not really skilled enough to do this properly, I suppose, but there's not a lot of information out there about this, and I thought it would at least help people get an understanding of it, and maybe someone can help me and explain it better to me. But anyway, we're going to be looking at a basic example today. So let's have a look at it. So what are we going to be doing today? Well, we've got this test code called CPC CRTC Rupture Interrupt. This is going to do a rupture split screen, and it's going to work on interrupts. And the reason I've done this is because all of the code works within the interrupt handlers. As long as your code doesn't disable interrupts, you shouldn't need to worry about how the rupture is being created in order to use the code. I'm hoping this is kind of a beginner's rupture example that you don't need to really understand the technicalities of it, and hopefully you'll just be able to use it as is. If you start messing with the code, then you start getting your screen shaking and you have to start worrying about whether it works on all CRTCs again, and it's not pleasant. So we're going to be compiling with Win8 today. I'm using my Notepad++ here just because it looks nicer, but let's compile this into the code here. So this is now completed, and all I need to do now is, if I just get my window here, do call and 8000, and we'll just see what today's code does. So here you've got the screen. Now we've got these sections here. Now all of these sections are showing different things. You've got these three showing this mode 0 section, which is why the text looks a bit weird, and the colors are inverted because it's a different memory address. You've got this changing part. Now this is, I think this is hexadecimal C000, and this is hexadecimal 4000. So they're actually showing different memory areas, and they're showing them in different screen modes. Another thing you'll see is that the top one and this third one here are moving in opposite directions. This is a hardware scroll being affected by altering those memory addresses, and this vertical bouncing kind of scroll here is also being done by changing the memory address being shown. These aren't software scrolls. You can see, however, that these two areas are changing, and you can see that the text isn't really changing that fast, and that's because a lot of our processing power is being used by those screen mode changes, which we'll see in just a moment. So what have we got here? Well, effectively we've got 6 interrupts, and we're managing to achieve 5 ruptures here. So we've got 5 different split screens, each of which is changing the screen mode, and each of which is using a different memory address. And in some cases those memory addresses are being altered by the code to simulate scrolling. So there we go. Now this is what we're going to be looking at today. We're going to learn how this example works, and of course if you just change the code, if you look at the code here, you've got a lot of test code here. You've got this infinite loop here, and all of this is just affecting that scrolling effect. Now we're not going to be looking at that today because this is really just test code. The idea is you'd replace this with your game or with whatever you wanted to do. It's going to be the section from this leave this part alone. This is the code that's doing the dirty work of changing the screen positions and redefining all 6 of these screens, because there is a 6th screen that's invisible on the top and the bottom here, and that's what's actually giving the rupture effect here. So we're going to be looking at that, but first of all let's have a look at some of the options that we've got. So that was kind of the default settings, but we can make some changes here. Now if I disable this make borders option here and I just recompile again, you can see now we've got a very small screen right at the top here. Not very useful, but I've left the option in anyway. We'll just reset that and disable that because I don't really think you probably want that, but I just thought I'd put it in there. So we're back to normal now. And one other thing to point out, as I said before, is you do need to make sure if you're going to write your own code or modify this, that it works on all CRTC types. So you can change them here. One thing you might need to be aware of though is changing them on the fly here does work in some cases, but I did find some cases where the code would work fine when you just did it on the fly, but when you reset and then ran the code again, it would no longer work. So you do kind of need to do both. I should point out I'm in alternating between call 8000 and call 1000 here. That's because the other 7000 bytes have nothing in them, so the memory is actually being compiled to 8000. But so as I say, you do need to just reset and test quite thoroughly. There are some problems with the timing of the interrupt, seems to be very slightly different as well, which I've not quite worked out how to get around, but in this case the code today isn't being that tight that it is going to be a problem with just very, very slight differences in the interrupts. So anyway, that's what we can do with regards to disabling the borders. We can of course change these memory addresses to alter the actual source data, but what we can also do is if we rem out some of these lines, we can actually turn off the screen mode changes. So if we just rem out of all of these here, so now we've only got 2 screen mode changes on 2 of these rupture blocks. So you can see now the bottom half is all in mode 0 and the top half is all in mode 1. And you can also see it's running a lot faster. This is not a coincidence. Now you see the ruptures, the screen address changes are all being done by the interrupts, but because those address changes don't occur until the end of the last screen and we're defining them very slightly earlier, if we change the screen mode at the same time, the screen mode change and the memory address change wouldn't occur at the same point. So what we need to do is we need to do a delay with no ops to get to that point. So the more screen modes changes you make, the slower your code is going to be. So the original test code had lots and lots because it was fun, but practically speaking, the fewer screen mode changes you use with this code, the better. Now I should point out you don't need to use Rupture to change screen modes. We did a screen mode change every single line in the EGX example, but if we want to actually have a split screen effect, then really you do need to, if you're going to use hardware scrolling. Of course, if you're using software scrolling, it doesn't matter, does it? But for hardware scrolling, you do need to do that. So there we go, we can change our screen addresses just by changing these, and these addresses are being changed on the fly by the code down here, and that's what's affecting our hardware scroll. So let's have a look at the actual code that's doing the work today then. So first of all, we've got the definitions we just saw here. We can rem these out, we can rem this out. We can't rem these out because they're hard coded in, but we can change them and we could make some of them irrelevant if we set the addresses to continue to wrap into each other. Now this is just test code, we're not going to go over this because it's not really very relevant here. All that you need to understand is that we're changing the addresses within the code that we're going to see later on. Now the serious work occurs here. This is the starting routine that starts setting things up. What we've got here is we've got some modifying code that is changing the interrupt handler within the memory. So at hexadecimal 38 we're putting a jump, and then at hexadecimal 39 we're putting the address of interrupt 1, the first interrupt handler. So we're going to use self-modifying code each time to change the interrupt handler as our code progresses. So when our interrupt handler starts, the first time it will run to here. We then self-modify so that the next interrupt that occurs jumps to interrupt 2 instead. So we're modifying that address in. And then we've got some code for the make borders here. Now, when this happens, the vertical sync will not actually have occurred just yet. So what we're going to do is we're going to, if we need borders, effectively force a border to appear. Then what we're going to do is we're going to wait for the Vsync. We read in from port F5, and reading in from F5 anything in this case will work, so F501, F5FF would all work fine, so we're only setting B. We then testing bit 0 and we're waiting for the Vsync to occur here. Once we've got to this point, the Vsync has occurred and we now need to wait a little while for the Vsync to finish. So we've got a little loop here around some no ops here. Okay, so at this point the Vsync has now occurred. So this is where we're now defining the first change to our screen modes. Now, because each definition is happening during one of the screens, we're actually working one change ahead. So interrupt 1 is defining the screen that is going to be visible during interrupt 2 and so on. So we're loading in address 2 here into HL, and then we're changing the registers that affect the address. So that's R12 and R13 here. So we're changing them both here using this address in here, and we've got some self-modifying code pointer here so that if we want to change this address on the fly we can just use this to do so, and that's what we're doing to affect that scroll. So at this point we've now defined our address here. We also need to define the height of our block. Our first block is 6 characters tall. You can see here we've got characters 2 to 7 here, so that's 6 characters tall. And so here we've defined the height of our screen. Here we've defined our memory address, and then the last thing we need to do is we need to disable that Vsync because we do not want that Vsync to occur until we've defined all of our screens. So we've set the Vsync to 255, which is impossible, so we're not going to get a Vsync now. And then what we're doing here is we're defining the screen mode for the first interrupt block. Remember I said that these settings will not apply until the end of the current screen because we're actually still drawing the top first sixth of the screen here. but the screen mode change will happen at the end of the current line. Now, technically speaking, at the point that this code is executed, we're probably actually not within the visible area of the screen at all. So we now change the screen mode immediately, but then what we need to do is we need to actually wait until the start of the second interrupt and change the screen mode for that. And that's what we've got here. So we've got the delay here for the first screen, and then we've got the change of the screen mode for that second strip. And then again, if we've got the borders defined, we need to actually set the true height of the screen so that the borders will start appearing in the correct position at the bottom of the screen. So at this point, we've done everything. Now, this is kind of the template for all of the others. Interrupt 1 and Interrupt 6 are special. Interrupt 1's a little bit more complex because we're at the top of the screen. Interrupt 6 needs to reset up that Vsync because we're at the bottom of the screen. But Interrupts 2 to 5 are basically the same kind of code, and they just really repeat what we've already seen. So let's have a look at Interrupt 2 here. So again, we're loading the memory address of Interrupt 3's handler, and we're self-modifying that into the interrupt call at hexadecimal 039. And then we're setting the vertical total to the height of this block. We're then setting the address of the next block. Remember, Interrupt 2 is defining the size of the screen that's going to cover Interrupt 3's area. And then we are waiting again to set the screen mode for Interrupt 3 if we want to do another screen mode change. And once again, this is why the code is so slow if we're doing the screen mode changes. But without those delays, the Rupture address change and the screen mode change will not line up. So you'll have a weird strip that won't match. Now, if that's acceptable because that area is black anyway, then great, go for it. But for this example, I wanted it to all be neat and perfectly lined up, and this is the best way I could figure out of getting it to work. So that's Interrupt 2, but Interrupt 3 is exactly the same as in Interrupt 4. Here's Interrupt 5, and then here is where things change again, Interrupt 6. So we're now at the bottom of the screen. So we now want to make sure that when this interrupt finishes, we do have some borders. So we're defining a proper height for a border here. And then we are now defining the memory address of the first block because, as I said, we're now at the bottom of the screen. When the next interrupt occurs, we want the first screen to draw. So we need to define the definition of that screen. So we're defining the address of Interrupt 1 here, the height. Now this one could be invisible just depending on whether those borders are enabled or not, but anyway. And then we're defining the memory address here. And finally, the last thing we're doing here is we're setting the Vsync position. We're effectively forcing the Vsync to occur at the end of this block. And that's really the end of the code here. So between all of these interrupt routines, the screen is split into 6 strips, or 5 if that 6th one is effectively a border. But this allows us to effect a split screen with mode changes and with address changes, and we can have hardware scrolling work independently on all of those, as you saw. Now, this is a relatively simple example. I know it probably doesn't look like that, but this is a relatively simple example of Rupture and of how we can do split screens. But hopefully this version will work pretty easily if you're a beginner and if you don't want to worry about the complexities of the CRTC rules, and if you don't want to do the debugging, because it took me about a week to get this stable on any system, and then it took a lot more work tweaking the code to get it working on all of the CRTC types. As best as I know, it works on all of them. But I should point out, I don't have a CPC monitor anymore. I'm only testing this on emulators because I only wrote this as a tutorial code. I'm not putting it in any games I'm using, so I'm not really willing to spend the extra time testing it on physical hardware, and it would be especially difficult because I don't have an original monitor anymore. Anyway, I hope you found this interesting. Unfortunately, we're going to go even further than this. Next time, we're going to look at using Rupture to effectively use 2-line pixel tall screens, and we're going to use this to synthesize a screen where the same lines are shown lots and lots of times, and we're going to warp that to have some interesting effects. So we're going to look a bit further, and I'm hoping that maybe one day I'll be able to do an RVI tutorial. RVI stands for Rupture Vertical Invisible. This is where you have screens that appear off the screen, and the reason you do this is to manipulate the source address. Now, when we're doing split screens like this and we're pointing to different chunks of memory, it's not too bad. But if we had screens that were just a line or two tall, we're quite limited in the memory addresses that we can specify as the source address. effectively we can only specify a limited number of source addresses, and we need to trick the screen into using the other addresses, and that's what RVI does. It has invisible lines that you can't see that trick the screen into showing alternate start lines, and it can also be used to manipulate the point that the interrupts visibly occur on the screen, because as I said before, the interrupts occur every 52 lines, but maybe there were 5 lines hidden off the side of the screen that you couldn't see. Unfortunately, the timing has to be very, 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 very precise, and I can't get it to work. So we're not going to be able to look at it, at least at this time, but I'm hoping maybe one day I can get it working, or if anyone wants to help out and offer me any source code to help me along, then please let me know. Anyway, thanks for watching today. I hope you've enjoyed this and hope you understood some of it, and goodbye.